So, let me now go to another new method. So, this new method, so suppose we have also seen functionals which has more than one independent variable. So, in that case the Ritz method changes to a much more general method known as the Kantorowicz method. Okay. So, if we have more than, so let me call this as method 3. So, if we have more than one independent variable, we are going to use the so called Kantorowicz method, right. More than one independent variable. So, we have so called Kantorowicz method. So, what exactly is Kantorowicz method? So, it is an extension of the Ritz method. So, for example, we have a function of two variables. So, we approximate our function of two variables as follows. We approximate it as Zn of x comma y, where now my basis functions are both functions of x and y, but notice how I write down my constants or the unknowns, summation I from 1 to n C I of phi I of x comma y, except that the only difference now in this approximation is that these constants are C I's are no longer constants, but functions of the variable, one of the variables x. Okay. So, again we choose phi of x naught y such that it satisfies the boundary condition, the same principle as we did with Ritz method, or let me say that phi 0 of x y is equal to z 0 of x y for all x comma y on the boundary of the domain, right. And also I choose my phi i's of x comma y such that phi I satisfies homogeneous condition, that is phi I of x comma y is equal to 0 for all x and y on the boundary as well, right. So, it vanishes on the boundary. Okay. So, now since we have chosen C to be functions of one variable, it provides us to choose a larger class of functions. So, this method, the generalization of the Ritz method has provided us with more flexibility here. Okay. So, as I said, the major difference is CI's are now function of one variable, they are now functions of one variable, and it allows a larger class of functions to be used. Now, so far we have seen the approximation. This question is, how are we going to use this approximation? Okay. So, notice that my original integral is the double integral. So, I am going to first integrate one of the integrals. So, I am going to integrate let us say the inner integral or the y integral. Okay. So, what I had is, let me say that let me say my approximate integral is f of Zn. This is also equal to the double integral over the domain omega of Zn of x comma y dy dx, right. So, we can easily approximate the y integral. We will see that and replace Zn with its approximation. We see that this is going to give us the following. Let me rewrite this stage slightly below. So, this is also equal to the double integral over omega times the summation phi 0 of x y, right, plus well certainly well phi 0 of x comma y times summation C I of x times phi I of x comma y, right. This is also equal to dy dx. So, this we can change into, we can take out, well first of all we have the integral over x, and then we have the inner integral over y of phi naught dy. This we can perform, and then notice this second term, we can take the summation out, and then we have the x integral C I of x dx, and the inner integral is from y 0 to y 1 of phi I of x y. With respect to dy we integrate, right. So, we can certainly perform the y integral on both the sets. So, what we do is we integrate the inner integral. The inner integral let us for the time being assume, that that phi is 0. Anyway, it vanishes on the boundary. So, let us assume that phi, the first family of the basis function, is 0. So, notice that now my approximate integral becomes f of z n is equal to the summation I from 0 to n integral of C I of x, and now the inner integral we can very nicely integrate with respect to y to get a function capital phi I of x dx, right. Let me call this expression by A. So, A is an integrand. So, notice that the integrand in A is purely a function of x, right. So, the integrand is purely a function of x, right. So, now we have changed a functional of two variables to a functional of one variable x. So, from here we can start applying the standard Euler-Lagrange machinery, right, to get the exact or solution with respect to the variable x, or approximate solution with respect to the variables x, y. Okay. So, let me just highlight through an example as to what I just said, right. So, this is my third example. So, again so this question says extremize f of z of x y, which is also equal to integral from minus b to b, integral from minus a to a of z x square plus z y square minus 2z dx dy, right. So, right now let me just interchange my x and y. So, my inner integral is with respect to x and the outer is with respect to y, right. Okay. So, we have to extremize this. We know that the Euler-Lagrange solution to integrands having two independent variables x and y is as follows. So, note that my Euler-Lagrange equation reduces to the solution of the following equation: partial x partial f partial z x plus partial y partial f partial z y is equal to partial f partial z, right. Okay. So, z, we further assume that z is 0 on the boundary, it is 0 on the boundary of this functional. Okay. So, when we plug in the value of f, which is this quantity, we see that this is also equal to del square z of x comma y. This is equal to minus 1. So, my Euler-Lagrange equation reduces to the Poisson equation. So, this is also the Poisson equation, and all we need to do to find the extremal is to solve this Poisson equation here. Okay. So, now we are now going to solve via the Kantorovic's method. Okay. Well, students can definitely solve this Poisson equation subject to the zero boundary condition. We are now going to highlight the solution via the Kantorovic's method. Okay. So, let me just approximate z by z1 which is also equal to c1 of x times b square minus y square, right. We note that z1 of x comma plus minus b is also equal to, the way we have chosen z1, it vanishes on the boundary plus minus b, right. So, now our approximation is such that we are now left with two more boundary conditions, that is at x equal to a and minus a, which we will utilize later on. So, we have already utilized two boundary conditions, right. So, then we have to evaluate these things. So, z1 of x, the x derivative of z, and we have to find the square of this quantity. We differentiate with respect to x, we get c1 prime times b square minus y square, and we take the square. Similarly, well, I can still go ahead and open this. So, this one becomes c1 prime square times b square plus, well, b4 times y4 minus 2b square y square, right, and z1 of y whole square is c1 of x times, we differentiate this, we get 2y, negative 2y, we square this up, we get c1 square times 4 times y square, right. So, I see that my f z can now be approximated with z1, right, and my f z is originally this integral. So, let me just write down this integral, right. So, this is now approximated. So, this is my f z. So, this is now approximated using my z1, and we see the following integral. So, I get integral from minus a to a dx of, I have now pulled in the y integral inside because that can be integrated immediately, and the inner integral is from minus b to b c prime of x square b square minus y square whole square plus 4 c square y square minus 2 c b square minus y square, and this is also equal to, well, this whole quantity is integrated with respect to y, right. Okay. So, when we do that, let me write down the final integral. The outer integral of course cannot be evaluated, but the inner integral after its evaluation gives the following result. We get a polynomial in terms of x. So, 16 by 15 b5 c prime of x square plus 8 by 3 b cube c square x minus 8 by 3 b cube c of x, right, and this is the integral with respect to the variable x. So, now we have reduced our two variable functional into a one variable functional, the variable being x. So, now the standard Euler-Lagrange machinery is going to apply. Notice that my f of z1 is now an integral from minus a to a of the small function f of x comma c prime. Well, yeah. So, c is my dependent variable. Instead of y, we have c as a dependent variable, right. So, then we use the Euler-Lagrange machinery. My f of x comma c prime is this following quantity. So, let me just quickly write it down. This is b to the power 5 c prime of x whole square plus 8 by 3 b cube c of x whole square minus 8 by 3 b cube c of x, and we see that when we take the derivative of f with respect to c, 16 by 3 b cube cx minus 8 by 3 b cube, I get that del f del, I am just evaluating the various partial derivatives which are to be used in my Euler-Lagrange equation, right. So, del f partial c prime gives me the following quantity 32 by 15 b to the power 5 c prime of x, c double prime of x, right. Let me further differentiate with respect to x. So, that is what we get. Okay. So, then well, let me keep these two terms separate because I need both the terms. So, this is c prime, and also the total derivative of partial f partial c prime is 32 by 15 b to the power 5 c double prime of x. So, we use all these in my Euler-Lagrange equation d dx of partial f partial c prime minus partial f partial c, and we see that we get the set it equal to 0, and this gives the following equation c double prime of x minus 5 by 2 b square c of x is equal to minus 5 by 4 b square. Now, students can notice that this is a constant coefficient non-homogeneous ODE, and let me write down the solution. Let me call this as my star. So, the solution to the star is as follows. I see that the solution, I directly write the solution. I get that this is C1 cos hyperbolic of square root 5 by 2. Students are asked to check that this is indeed the solution or find the solution themselves, which is not difficult to find for the ODE. So, this is square root 5 by 2 x by b plus half. Okay. Now, we also know that c of x, we also know that z is 0 on the boundary, right. So, z must be, z is definitely, the solution is definitely even with respect to y. So, z is an even function with respect to both x and y due to the presence of the boundary condition that we have, and also the type of the functional that we have, right. That is easy to check, right. And so, which means that we can completely, using this condition, we can completely eliminate K2, right. Even if we do not know the symmetry, even if we do not know that z is an even function, we can use both the boundary conditions, not a problem. Right now, I am just simplifying. So, now we only have one parameter to solve for, that is K1, and we also know that this is given that z of plus minus a comma y, the solution vanishes on the boundary. So, I can very well use the fact that c of a is 0, do not need to use the other boundary condition because we have already used the fact that z is an even function. Okay. Once we do that, we see that the solution comes out to be, which is approximated as z1 of x comma y. Let me write down the solution. This is half b square minus y square. So, that is the y dependence times 1 minus cos hyperbolic of square root 5 by 2 times x by b divided by cos hyperbolic of square root 5 by 2 times a by b. Right. Notice that this vanishes on the boundary x equal to a. Now, I end my discussion here by mentioning that we could possibly use more and more approximation for a better resolution. So, for more you know, or better, the word is for better approximation, we could possibly try this form of the approximate function b square minus y square times c1 of x plus b square minus y square whole square times c2 of x, right. So, this is for a better approximation. Okay. So, I end my discussion by giving a reference in which more and more numerical methods and better numerical methods are prescribed. The students are asked to refer to this book. So far that we have shown in this lecture is all preliminary, and students are asked to refer to this following book, Calculus of Variations by L. E. Elskog. Elskog. Okay. And then there is another paper in Proceedings of Royal Society A, volume 303, page 497 to 502, and this is a very classic paper in 1968. This mentions some of the numerical methods to the Euler-Lagrange equation. So, thank you for listening, and in the next lecture I am going to talk about isoperimetric problem or constrained optimization. So, thank you very much.